Can you write something as order for this?
We'll make sure.
I can't remove it now. I can't remove it now.
Why?
You said if I do the focus on the book.
Yeah, but if you start writing, then you can remove it later.
Okay, let's start. Mic. So, I'm going to write down a bunch of things, and, well, we'll see in a second. So you all know what binary search is? Yes? Okay. You also now know you know what this is now, hopefully. How many of you are also in machine learning? Not too many. So the few of you who are, have you covered boosting yet? Does it sound familiar?
Yeah, we're just starting.
You're just starting boosting? Okay, so you're about to start? Okay. So then, those of you who are in the class have heard of boosting. So I'm going to write that down as well. Are any of you familiar with game theory? Have you heard of algorithmic game theory? A little bit, vaguely? Yeah? So I'm going to write that up here. Okay. So of course these are four concepts very different from each other that you've all heard of. The last concept is also very different from these. And you've heard of it too, but it's different in a different way. Zombies? Yes? I wanted to do this last week for Halloween, but I missed my timing on this. So zombies, binary search, linear programming, boosting, and game theory, they all have something in common. And the question is, what is that thing? The thing that they have in common is the thing we're going to talk about today, which is a very mouthy thing, which is what we're going to call this is a technique for algorithm design that has been around for a very long time. It's one of those techniques that keeps getting reinvented in different communities, and that's why it shows up in many different places. It has many different incarnations. It looks very different depending on where you're coming from. But at the core of it is a very simple idea. So simple that people are beginning to say now that this should be taught the same way we teach divide and conquer, dynamic programming, and other sort of core concepts. It's as much of a core concept as these. But because it's a little bit more specialized, it takes a bit more background to get into it. But there are zombies, so it's all good. And I'll explain why the zombies show up in a second. And that's what I want to talk about today. Multiplicative weight update method, and how it can be used as an algorithm design principle. It's we're moving away from LPs. We've sort of finished our sort of unit on LPs, if you wish, with LP rounding. But they're going to make a reappearance again, and you'll see why. So it's not completely off what we're talking about also. So the story of where multiplicative weight updates comes from starts from a very simple question that you can in fact solve using binary search or something that looks like binary search. And that problem is called okay. And you may have heard this phrase as well. This is again, machine learning, this kind of setting comes up a lot. And the basic setting for learning from experts is that You have a question. The question could be, will it snow again in the next half an hour before we get out of, or the next 1.5 hours before we get out of class? Will it rain tonight? Will the stock price of Apple go up or down? So to keep things simple for now, let's pretend we have a question. And the question has a 0-1 answer. And we'd like to predict that answer. Because if we can predict it, we make money, or something good happens. We don't get wet, or whatever. Right? So there's some kind of question, and you can think of this as the question being asked every day or every minute, whichever time unit you want, but it's being asked over and over again. And you keep making answers, and you measure how many times you make a mistake. Again, in the machine learning world, this is often called online learning, or the measurement is called the regret one, and I'm not going to get into that. But it's a very simple model, right? So I make my prediction, I check the actual answer, so I wear my coat thinking it's going to rain, doesn't. So it's okay, I made one mistake. Tell that. Next day, do the same thing again. And of course, you'd like to make as few mistakes as possible in this process, because every mistake costs you something. And so what you have at your disposal is a battery of experts. You know, all the weathermen, all the weather stations that cover Utah, or a whole bunch of stock picking advice coming from strange email addresses that end in strange extensions. Maybe you should use those. And you ask them for their opinion. And you want to somehow use their opinion in some kind of systematic way to make better predictions for yourself. In particular, what you'd like to do, since you don't know anything except what the experts are telling you, what you'd like to figure out very quickly is who the best expert is, and go with what they do, because that's the best you can possibly do. So this is the learning from experts problem, where every expert has some information about a problem, and you want to know who the expert is. Okay? So let's start with the simplest setting possible. So there is always suppose I promise this to you, that in that pool of experts you've assembled is one person who's always right. You want to find that person. What should you do? And the goal here, remember, is to find that person as quickly as possible, by which I mean making as few mistakes as you can. Right? There are many strategies you could imagine for doing this. And in all cases, the model is you ask the experts for their prediction, they make the prediction, you observe reality, you do something. And then this repeats. And you count the number of times that the action you took based on the predictions was forward. Does the question make sense? So the question is now, given this assumption, what is the best, well, not the best, forget the best. What is something that you could try to do? And again, the goal is not to be, we're just thinking. So we're not trying to do something really clever here. Yeah.
So are we just trying to, do we know the actual answer to the problem, or are we just relying on experts?
What happens is that after the experts give you your prediction, so the experts all say it's going to rain, you put your jacket on, you open the door, and you see.
Okay. So we know the actual answer then.
After you made your prediction. You can use that information to maybe guide you the next time. But the sequence of events is ask for predictions, make your decision, see reality. And then back again. Ask for predictions, make your decision, see reality. Yeah.
Is the correct answer discrete or continuous, or is it like just true or false?
Correct answer is the correct answer in this case is assuming a true false answer.
Oh.
Let's assume that on every cycle there's a true false answer. Then you can make this more general, but for now we're just taking that. Yes?
So every time that you ask a question, you go and see what the actual result is, so you can get the experts that make the wrong prediction, and then you just continue on saying, how about that?
So tell me the protocol. So you ask the experts for their opinion. So some experts say true, some experts say false. What is your decision?
You decide the majority, and then you,
Take the majority.
and then you can go out, and then you can see if it's,
And then what do? You look at all the experts that were wrong, you throw them,
yeah.
right?
And
If you made a
then,
mistake.
and then you just keep on going until you.
Good. So let's write down the strategy. So the strategy being proposed is this. This is the proposed algorithm. Okay? So we ask the experts, yes?
What if the experts just end up with a tie? I mean, the half to half.
With the two left experts?
Oh, no, I mean, all the experts, they can divide into half and half. If their predictions are just.
What do you think we should do?
So our algorithm cannot go on.
So what should we do? Fix it.
That's the point.
What should we do if it's half enough? What do you think we should do? Don't think too much. What do you do? What do we reason?
Maybe just drop that example and take the next one.
Suppose this keeps happening.
Uh,
Yep.
Can you just hold one vote until you check which one's correct?
You could. So one option is drop the example. One option is hold on to both and then take another example and wait till you get as you're saying, right? You take another example and see what happens. Or say keep all the experts who are
Well,
tied.
you can verify after, or do you have to pick one before you verify?
Well, you have to pick. No, you have to pick the decision. Are you going to put the code on or not? Right. So, but you could keep them. Yeah. Yes.
Are we trying to get the right answer each time or find the expert as fast as possible or both?
The goal is to find the expert as fast as possible.
Okay, so it doesn't really matter if we're right or not.
But you want to well fast as possible mean in terms of the length of time is the number of mistakes you make.
Oh, okay.
Yeah. Sorry.
And is that in terms of the number of queries to experts?
Let's say in terms of number of mistakes. So, but we still have this tying problem. What should we do with the tie problem? Because the algorithm is not fully specified. Yes.
Can you just simply flip a coin and go with that?
We could. So we have three solutions. We could flip a coin. We could just ignore the example, or we could keep them around and just not do anything with them and wait for the next one, which is, I guess, equivalent to ignoring the example. So we have options here. So we'll figure out which option we need once we figure out what we want this to do. The first question I guess we should ask ourselves is, how many mistakes are we going to make before we find the expert? Let's say there are n experts. Yes.
It depends how often the other experts are running.
It does. So the question is, can we still, in spite of that, say something? Regardless of what we know about what the experts are doing and how wrong they are and how often they're wrong, knowing only that there is always one expert who's always right, and given this protocol, with some reasonable way of adjudicating ties, can we say how many mistakes we're going to make before we're done, before we find the expert, or that we'll find the expert at all? That's the question. That make sense?
Yeah, you could have an expected.
Sorry?
You probably could have an expected based on the probability.
But are there any probabilities here?
I mean, how often the right is a probability?
We don't know that. This could be adversarial. The only thing I'm allowed to assume is that there is this one expert. Everyone else could be wrong in some weird way. I don't know anything about it. So we could use a randomized argument, but we need to introduce randomization somewhere because there is no randomness inherent in the problem. Yeah.
So if there are n experts, you'll make n minus 1 mistakes.
You'll make n minus 1 mistakes. So you will make, are you saying you'll make at most or you'll make at least?
At most.
You'll make at most n minus 1 mistakes. Why is that?
Because the worst possible case is that whenever you make a mistake, that means that at least one expert was wrong. And if you take the minimum number of experts equal time, there are n minus one of them before you reach the last expert. So the worst possible case is one expert was wrong, and the next time another expert was wrong, and another expert, but all of the experts right. So it'll take n minus one steps.
So you are correct that n minus 1 is an upper bound. It is not tight, and the answer is hidden in what you exactly said. So let me go around. Oh, you want? Oh, so let me get another one thing.
Okay, it would be something like log of n, because if you did get something wrong, half or more of the next person would have to be wrong.
Okay.
So
So the point you had a good point that you're saying, okay, we need to figure out how many experts will be wrong every time we make a mistake, and you correctly said that, well, at least one is going to be wrong. But in fact, you could be a lot more aggressive because you're taking the majority, and that's why the majority is that what you were going to say? So because you're taking the majority, you know that if you're wrong, half of them are wrong with you. You just like get them out of there. Okay? Yes.
This could be adversarial. So
This is adversarial.
so then the adversary can make it so at most there's one wrong every time.
But then the majority answer. I'm taking the majority answer. If one expert is wrong and all are correct, I'm going to get the correct answer. So I'm good.
Yeah.
So I don't charge myself for correct answers because I don't get wet. I only charge myself for wrong answers. So I could have a long string of successes. I'm not going to pay for those things. So it's not time. That's why I said it's not time. It's number of mistakes you make.
Say mistakes, not rounds.
Right. But you would be correct that if you tell me on one wrong, then you could be going on for, but then you'll be fine. You're getting the right answer. That's not polite. Yes?
So I think it's about the log, the time, because every time.
About?
I mean the log.
Log of n. Yeah, that's what
Yeah.
I think Craig was saying. Log n. Yeah.
Yeah, so because every time we have more than half to be done, the expert, and finally we will remain the one.
Right.
Yeah.
So the idea that all of you are coming up with, which is very good. So you're basically saying that if I pick the majority answer and that's wrong, I have a lot of witnesses of wrongness, of being wrong. And they will all have to be discarded. So at least half, and by the way, this is why it doesn't matter whether I have a tie. Because all I want to stay is that I get rid of half. If it's exactly half or slightly more than half, I don't mind. So it doesn't really matter how we break ties here. Because if they're tied equally, and when the answer is wrong, then I'm going to get rid of half of them anyway. So I get rid of half, I do this again, then maybe I get a few correct answers, and I get the wrong answer, half of them are gone. So in log n mistakes, I will get the correct answer. Yes?
So the answer could be, like, is definitely true or false, but are there only two answers? Could it be raining, snowing, or sunny?
We're going to generalize this like crazy.
Oh, okay.
I mean, we haven't even got to the zombies yet, so.
I just wonder if this algorithm is really good in practice. Like, it's really.
You know we're not allowed to ask that in this class, right? We don't care about practice, no, I'm just kidding. So when you say not good in practice, what do you mean?
I mean, because we may have the condition that I have said before, like a tie or something.
But tie is okay because you'll get rid of half, right?
And we could not go on. Like,
You can, because you just get rid of half.
but
So they tie.
half-
Doesn't matter, take any answer. So if you take any answer you want, if it's the wrong answer, you still get rid of half of them, right? It doesn't matter which answer you take. So half of them said yes, half said no. You just took them no, you got wrong. Okay, so you made one extra mistake, but you lost half of them. So instead of maybe log n, it's log n plus 1. It's not going to make a big difference.
Okay, so we don't consider about the noise of the example.
We will. Just 1 second. Good. I'm glad you brought it up. There's the noise an issue. But first, before we do that, I want you to recognize within this learning experts framework a very familiar concept. I wrote down those things on the board, right, in the previous slide. What does this remind you of? Or what should this remind you of? This process. So other things are reasoning about this process.
Divide and conquer.
Divide and conquer, and more specifically, binary search. Very good. Why is this like a binary search? Think of the expert as the thing you're looking for. Okay? So what do we do in binary search? So, okay, we'll take the middle point. Somehow we got the middle point, right? Either we're doing a median search or something else, we got the middle. And now we want to see whether the middle is bigger or less than the thing we're looking for. Why are we looking at the middle point? We're looking at the middle point because we want to be sure that no matter which way the answer turns out, we can eliminate half of the things, right? And that's exactly what's going on here. We're saying that if we get a wrong answer, we can eliminate half of the input. So you can narrow down, okay, my expert is here. You narrow down some more, okay, my expert is here, and you find it. So essentially, this is a binary search in disguise. It's got all this learning from experts and weather reports and stock tickers and stuff on top of it. But really what it's saying is that there is one little glowing expert in your pile, and you're kind of zooming into it using this procedure. Okay? So this is glorified binary search. Okay? So far I've just recast something that is very familiar in a form that's very unfamiliar. Just made life difficult. But there's a reason for this, of course, because we're going to try and say, okay, you start with binary search, we're going to lift things up and make them more complicated. Okay. So how can you make things more complicated? And you've already alluded to this already. What happens if experts make mistakes? Suppose we no longer have the guarantee that there's one expert that's always right. Will the same procedure work? So I just remove the guarantee, so I don't know any of the experts. But I want to find the best expert, the one who makes the fewest mistakes. Will that algorithm, will this work? Yes?
My intuition would say no, because what if your best expert makes a mistake early on in the majority of the field?
It's gone. You know, one strike and you're gone. So it won't work at all. So this method, while it's, it's great if you have an assumption, is very fragile. If your best expert makes even one mistake, you can no longer guarantee that you'll find the right answer. Even if the best expert made one mistake and everyone else makes 100 mistakes all the time, you still cannot be sure you'll find that one expert. It's not a robust method. So the question is, how might you make this a little bit more robust so that it can handle the case when experts make mistakes from time to time? So you've all heard of 20 questions, right? The 20 questions game. Guess a number between 1 and 1,000, binary search. Have you heard of 20 questions with a liar? No? So von Neumann proposed this game many, back when von Neumann was in the 50s, right? So this is 20 question a liar basically says that you're asking someone to think of a number, and they tell you, whether your guess is hot or cold, but they lie from time to time. And so let's say they're allowed to lie, 5 times, and the number's between 1 and 1,000. How many guesses will it take you to get to the right answer? That's sort of the setting we find ourselves in now. The 20 questions with the liar example, where they're not necessarily lying intentionally, but they make mistakes. And so your regular binary search no longer works because of this problem. You have to think of a different way of doing your binary search. Yes?
It seems kind of similar to like cache problems where the question is like, when do I get something from the cache? And you give it another chance, even though like it should be a bit times. It seems similar to that.
So you mean you ask the cache a couple of times to see whether it's in there or not?
Oh no, like if you were going to evict something from the cache, but you don't know if it'll actually be used very shortly later.
Yeah.
Then I know there were like some replacement policies where like you actually like give out like some objects, there's some items in the cache like an number of fans to stay in there, or like the prevent work.
Ah, I see. Oh, interesting. Yeah, that seems similar. I don't know if it's directly similar, but it does seem has a similar flavor to it. Yeah. Was there another hand up in the back? Yes.
You have a counter for each expert.
Okay.
And whenever the expert is right, just implement the counter.
Okay.
And find the expert with the majority of the right answers.
Ah, so you want to give them some kind of power. Like, you got the right answer 3 times, I'm going to trust you more than this other person who only got the answer 2 times. Is that what you're saying?
Yeah.
Very good, very good. So let's develop that idea, okay? Okay. So here's what we're going to do. We're going to start off with everyone having a weight, just as you said. So new idea, so start off with a weight for each expert. And we're going to say that the weight of each expert is 1 to start with. They're all, equally good. Okay? You should think of the weight as your level of confidence in the expert. In the beginning, you have no reason to mistrust them. They're all great. Okay. And so now what you do is, so let's actually take this entire algorithm. Okay? So the same algorithm as before, but I'm going to remove this step. In fact, I'll just erase this step. Okay? And here's what I'm going to do. I'm going to say, well, you made a mistake, but I'm a forgiving kind of person. I will keep you around, but I'm going to watch you. And I'm going to, reduce your importance in the grand scheme of things. So exactly as you said, we're going to decrease the weight. It turns out I won't actually just subtract 1 or increase counts like this. I'm going to do something slightly different, and we'll see why. But it's essentially the idea that you had, namely, so if they were 1, they become half. So this effectively does the same thing you wanted to do. It reduces the importance of experts who have made mistakes in the past. Right? And therefore, relatively speaking, increases the importance of experts who have made fewer mistakes. Right? So you'll start off with the model of 1. After 1 round, some of them will go down to half. Another round, maybe some of the ones who are 1 go to half, some will go to 1/4. You get this kind of distribution of things. And now when I say take majority, I call it a weighted majority. So one way to think about this is that if I have 2 experts with a 1 and 2 experts with a half, you can think of the 2 experts with the 1 as sort of double. So you double their vote. And the 2 experts with the half, so then you have a weighted vote. So this is a new algorithm that seems to at least be less fragile than the previous one. It handles the issue of noise, where experts might make mistakes. We still don't know how well it does, though. Yes?
So when you say repeat until only 1 left, is that when only 1 expert has a weight that swamps all the other experts?
Good question. That effectively is what will happen. 1 expert's weight will swamp everyone else. They'll become arbitrarily small. And there's some threshold where you have to stop. When the number is less than 1 over n or something. When their weight is less than 1 over n, you stop. That'll turn to be fine. So okay? So the question is still the same as before. How many mistakes do we make before we hone in on the best expert? So no, we're not trying to find the expert who's perfect. We're trying to find the best expert. Okay? So if you think about what's going on here, the basic idea is exactly the same as before. You are taking a weighted majority. Therefore, instead of the number of experts who tell you what to do being large, the total weight of experts telling you what to do is large. And so if you make a mistake, it's not the number of experts that drops by a factor of 2, it's the total weight that drops by a factor of 2. And since this weight is reasonably large to begin with, you are always making progress. Right? The reason binary search works is because you're saying, if I make a mistake, I significantly reduce my size that I'm working with. I go from n to n over 2. Even in this case, I go from n to n over 2. I make a significant difference in the size of my input. It's really small. Similarly here, if you think of the total weight, that's a number you want to say is reducing significantly at every step. And that's kind of what this is trying to capture, but in a more smooth way, right, than just saying you have the count of number of things. So the analysis actually works more or less the same way, but because you're dealing with weights instead of individuals, you have to be a bit more careful about what you do. So let's look at how this analysis is going to work. So is the algorithm clear? Does it make sense? Yeah.
Well, so are we still saying there's an expert that's usually right, or like how do we know that?
The expert that's the most right.
Okay.
The most right expert.
Okay.
So they're all making mistakes, right?
Yeah.
But someone gets it right, 9/10 of the time. It's like when you have the ESPN panel predicting the NFL games every week. There's someone on top. Yeah.
So what if they're right less than 1/n times? Most correct expert.
Yeah. It won't
That can't be
necessarily
right.
convert, will it?
They can't really be. They're inexperts.
Yeah.
So basically, they would all be wrong all the time, is what you're saying.
They're usually wrong, is what I'm saying.
So the bad case, the edge case you worry about is that they're all wrong all the time. So they start as 1, they all become half, they all become 1/4. So nothing actually changes, right? So let's assume that kind of weird edge case doesn't happen. Where you have all the experts being exactly the same all the time. If there's even a slight difference between them, you'll see that this will make a difference. Because intuitively, by dividing by 2, you're creating exponential gaps between these things. And that's what's going to help us here. So if there's even a slight difference in quality between the experts, it'll blow up.
So for us, we just give them a distribution of like true or falses, depending on the answers, or?
There's no distribution yet, but you're right that this W is kind of acting like a proxy for a distribution.
Okay.
Yeah.
Because, I mean, if we just take blocks of queries, then technically we could just happen to pick the ones that are always wrong, even though on average they might do like half of them.
I don't know what that means. There's no distribution of the queries. The queries are arbitrary.
Yeah. So if you just take arbitrary queries, you might always get wrong, even though on average one will be like half wrong and half right.
No, but if the expert, I think you're asking me, is the expert probabilistic?
Yeah, or is your query probabilistic?
Neither.
Oh,
Right now, neither.
okay.
There is no probability anywhere in this.
Okay.
Yeah.
Then I'm just curious how we're going to formalize ignoring that edge case, but okay, we'll probably get
We can assume that there's one expert who's strictly better than the others. That's one way to say this.
with respect to the queries you make.
Yes.
Okay.
Thank you. Right, and that would be one way to do it. Okay, so let's analyze this procedure. So let's look at to prove this, okay, so let's say M is equal to the number of mistakes we make so far. Okay, and let M be the number of mistakes made by the best expert. Okay, so this is a particular query sequence you can think of. We're asking questions, getting answers, we're doing the majority thing, and we're doing the weighting, and this and this. Okay? So we know that every time an expert makes a mistake, its weight goes down by half. Right? So we've gone through this process, we've made some number of mistakes so far, and in that process, that expert that we're looking for has made small n mistakes. So we know the weight of that expert, so let's call that expert I. Okay. So we know that Wi right? Because it started off with 1, I made one mistake, one mistake, one mistake, one mistake. But what can we say about the total weight? If you add up the weight of everything. So let's look at the total weight. Okay? What can we say about the total weight? Remember that we made capital M mistakes. If we have made capital M mistakes, then at least every time we make a mistake, at least half the total weight told us to make that mistake by the majority rule. and that half the total weight gets its weight reduced by half. Right? So it's not the total number of experts, but the total weight of those experts, which told us to make that wrong decision, gets their weight reduced by half. Okay? So if your weight before was phi, your weight now will be at most 3/4 of phi, because half of your weight loses half of its weight. So you effectively lose 1/4 of the weight. Does that make sense? Right? So what we're saying is that we had this weight, so we have to think of this as the entire weight, and this was half of the weight telling us to do a 1, right? And there was this other part telling us to do a 0, right? And we got it wrong. So if we took this part and we reduced it by half, this could be, half of the input. It's at least half of the input. Reduce it by half. So this half plus this 1/4 is going to be 3/4 of the total weight. Does that make sense? So every step, and this is the progress we're talking about, at every step, you go from your total weight to at most 3/4 of your total weight, which should immediately tell you this is a good thing. We're making a constant factor of progress every step. I see logs in my future somewhere. This is what you should be telling yourself. So the total weight we can say after m mistakes, right, is going to be less than or equal to the original weight, which was n, because we started off with all items having weight 1, times capital. Okay? So now you have to think of two races happening. There's the race to the bottom for the expert. Every time it makes a mistake, it loses by a factor of half to the n. There's a race to the bottom for the total number of mistakes. This is going down the rate of 3/4 of the n. What do we know about these two quantities? What can we say about these two quantities, the half to the m and 3/4 of the n, at any point in time? Remember that half to the m is the weight of one element. Phi is the weight of all the elements. Right? The weight of the sum is more than the weight of any one of the elements. So you should think of it as, this is your expert, this is us. We're all going down. At some point these things will catch up with each other. We can't go any further because of the inequality. When does that happen? So now if we solve this inequality for m and n, so one way to flip this around is to say that notice now that we have things exactly where we want them. We have the thing we're trying to compute on the left side, and we have an upper bound in terms of the thing we want to measure it against, the optimal number of mistakes. Right? Because think about it this way, what is the best possible thing you could do? The best possible thing you could do was somehow know who was the right expert and go with their opinion every single time. How many mistakes would you make? You'd make n mistakes, small n, because that's the best expert, that's the best you can do. So if we want to measure in terms of what's optimal, that's optimal. We want to see how good our strategy is with respect to that. Right? So now if we simplify this expression, we get that m is less than or equal to some constant times the optimal solution plus an extra log n term. Just by taking logs on both sides. In other words, why is this interesting? The number of mistakes we are going to make before we terminate is related to the optimal number of mistakes plus an extra log n term. You should think of log n as hopefully something smaller in relation to things. And in fact, you can't get rid of that extra term. There's always going to be an extra term. So again, the analysis is a little tricky, but the basic idea is the same, that you are making progress at every step. And at some point you will catch up with this other thing. Just like in a binary search, you'll catch up with one thing at the end. That's what it is. So notice that in a binary search setting, where m was 0, because the expert makes no mistakes, you just get log n, which is what Krishna lost. So this in some way generalizes that result. And so this is giving you a bound in terms of, so if you go back 20 questions to the liar, if your expert makes only k mistakes, you're going to get a bound that looks like this, log n plus k. There's a strategy that allows you to do that. There's no randomization here, it's purely deterministic. But again, using this majority rule, this weighting thing. The idea again, downweight the experts. And notice that, so going back to the point of, well, how do we know how much to downweight? You should see now that there's a reason we reduce by a factor of 2. Because you want these things to go down quickly. If you didn't reduce the weights by a factor of 2, you just subtracted a little bit from it, then this number would not go down quickly enough. It would take a long time to get to the right answer. So you have this balance. You want to be aggressive, of course you don't want to be too aggressive, which would be the original binary search case, but you want to be somewhat aggressive. So you don't throw them away, you don't set the score to 0, but you don't subtract only a little bit, you just divide it by 2. And that gives you the bond. So this careful balancing act is what's getting us between. Yes?
Did this work if, for some reason, you wanted to find like the best K experts instead of just the best expert?
I want to say yes, but I don't have a proof off the top of my head. My intuition is saying that if you're looking for the best K experts, what's going to happen is they're all going to stratify out, and the top K will be at the top with high probability. What I'm thinking about and I'm not sure about is what your termination condition is. When do you want to stop? My feeling is that at some point you will find the top K are significantly better than what's left, and then you just stop there. So what's significantly better is I'm not quite sure. But my gut instinct is that yes, they should work. You just have to change your termination condition a little bit, and then just read off the top K unit. So run a certain number of times and say, okay, after this point, it might be something like m plus log of n over k or something. I'm making this up, I'm not sure. But there'll be something you should do that. Yes?
I was just going to say, like, I don't know how it changes with the possible errors by it, but if they're all correct, then having k experts definitely works, and I believe it is n over k.
If they're all correct, then doing that does only
Yeah.
Yeah, because you just do binary search.
Yeah, we had this question in machine learning.
Okay, yeah. Okay, thank you. Any other questions? So, where are the zombies? So this is how I think about it. So I spent many months trying to understand this technique because I wanted to use it in a paper and I didn't understand it. So I was reading it over and over and over again. And this is, by the way, typical as you read your projects. You're not going to understand a concept the first 10 times you read it. It takes a while. And for your projects, you don't have to understand it as well as that because you don't have 6 months. But so when I started thinking about it, I realized that what's really going on is that in binary search, when you remove the items, you're sure you're correct about the elimination because they were wrong. In this case, you're no longer sure. You kind of have to, you're not sure if you can eliminate them. Essentially, you are killing them, but they come back to life. And each time they come back to life, they're a little bit weaker. They're about half as strong as they were the previous time. Then they come and bite you, and you kill them again. And then they come back up, and you kill them again. Eventually they die, but it takes the whole movie to get that to happen. And that's why I call this zombie binary search. You can think of these things you're eliminating as zombies. They come back, but they come back weaker each time. First you get an arm, you get another arm. I'm sorry, I'm very gruesome. I like that. That's why I should have done this last week at Halloween. And I'm not saying you should remember it this way, but I can guarantee that if you Google zombie binary search, the first link you'll come with is my blog post where I write about this from 3 years ago. And that was deliberate, so no one else has started that way. But it helps me understand what's going on. It helps me understand what can be a very baroque concept. If you read the lecture notes, they can be very complicated. But really at its core, it's a very simple generalization of binary search to the case of errors and how to think more systematically about dealing with errors. Okay? So, there's a slight variation on this. To get to the actual multiplicative weight update, you do a slight variation on this theme. You don't actually compute weights and take a majority. You do something slightly different. So let me take that algorithm again and change it. So when you do this analysis, this constant is a certain constant. You can actually make this constant a little bit better. And here's what you do. So I'm going to take this thing, this is our weighted majority algorithm. To get to actual majority, do something different. Don't do this step here. Instead, okay? So one small change. So as you've all been intuiting, right, these weights are acting like a kind of de facto distribution over the experts, giving you a sense of which experts you like more than others. Well, let's make that explicit. Normalize the weights as a probability. That means add them all up and divide by that. And then pick an expert with a certain probability. Instead of doing this deterministic clear, I just say, okay, let's take a vote and see who wins. Pick one with a certain probability, which allows you occasionally to pick someone, who had a low probability. That's okay. It turns out this actually improves your bound a little bit. You can show that the same analysis we did before can be made, but now you improve the constant in the number of steps by a little bit. And this, in fact, with this form, is what is typically called the multiplicative weight update. Yes?
Sorry, I was just wondering, what does the 2' say?
Instead of doing 2, which is take the weighted majority of the votes and use that answer, instead ask one expert what their answer is and use their answer. But the way you choose which expert to ask is based on this point also. So for example, suppose you have 3 experts. They all start off in 1. A couple of answers later. 1 expert. So let's write an example. So to do this one, so let's say we have 3 experts. Okay? At some point in the process, we did some things, and this one had weight, let's say, half. This had weight 1/4, and this had weight 1/8. Okay? Now with the weighted majority, you will always pick expert 1. Always. Right? At least for this question. For this particular step, step 2, you would pick expert 1. What I'm saying is, rather, normalize these things. So this becomes, so can someone do this for me? So that's 3/4, that's 7/8. So half divided by 7/8 is 4/7. That'll be 2/7, and that'll be 1/7. Okay? Pick one of the experts with this probability. So you pick expert E2 with probably 2/7, you pick expert E3 with probably 1/7, pick expert E1 with probably 4/7. Yes, 4/7 of the time you will pick expert E1 if you ran this, but sometimes you will not. Whichever expert you do pick, ask them, hey, what's your vote? And go with that. Does that make sense? So that's the change from 2 to 2 prime. You seem like you have a follow-up question.
I understand that part, I'm just wondering like what the notes that, like I couldn't read them.
Oh, you just couldn't read it, I'm sorry. It was a handwriting problem, not a clarification problem. So pick some expert probability proportional to WI. That thing is proportional. Proportional to WI and use their answers.
Sorry.
You pick one expert with probability proportional to their weight.
Okay.
And then use that whatever answer they give.
Okay.
Yeah? Okay. Good. Okay. So that's what this method is. You can fine-tune this even more. So I said reduce by a factor of 2, right? There's no reason to do that. You could actually reduce it by some epsilon. So instead of saying, so go back to the step here, instead of saying decrease weight of wrong experts by half, we can have a 4' that says decrease weight by a factor of 1 minus epsilon. So you reduce the weight just a little bit, not too much. You can think of this as being more conservative. Right? You don't want to, just because they made one mistake, you are really forgiving. So you're going from, total dictator to Mother Teresa. So this is the extreme of sort of things you have here. Right? So it turns out that if you analyze this more carefully, the number of mistakes you make becomes something like 1 plus epsilon times the optimal solution. So you get better and better to the exact optimal solution. But, and here's the catch, what is the catch? The other term starts going up. Intuitively, changing that epsilon factor says, how aggressive do I want to be about tamping down mistakes that I'm seeing? If I get very aggressive, in which case epsilon is 1, right? I just remove everything that's bad. I will get, I can plug this in here. There's something not quite right here, but if you think of epsilon as very large, you're aggressively tamping on things, that number becomes small, this number becomes worse. If you make epsilon very small, you are very conservative about eliminating entities, then this number becomes better, you get close to the right answer, but this number becomes very large. So there's a balance between these things. And that controls how exactly, depending on what you want and what kind of bounds you're looking for, you can control these parameters. So this is the full multiplicative weight update method with the epsilons and the probability. This is what it consists of. You take your experts, you do this weighting update, you pick something at random, go in and keep repeating. Yeah.
So let's say you had some other information in the problem, like if we're thinking about rain or not rain, let's say we also knew about the season, like fall or spring or whatever.
Sure.
And let's say you had like one expert who was really good with spring and one expert who was really good with fall.
Right.
Is this problem still like the same thing?
Yes, in the sense that, well, this problem is extremely general. It makes no assumption about how the experts get their knowledge. It makes no assumption about how good they are. It makes no assumption about how they're processing the data, whatever to do, whatever they're doing. So you can apply this method to that situation, and you will always get a good answer, but you can get a better answer if you paid much more attention to those experts. If you could break your experts into groups and say, okay, this class of experts makes mistakes this fraction of time, this group of experts makes mistakes this fraction of time, you might be doing even better. And in fact, there is a more general way of saying all this. Lots of questions. So, yes, one there.
And then would it be the same if an expert's so bad that you should say the opposite of what they're saying?
Pardon me?
Would it be the same thing if an expert's so bad that you should say the opposite of what they're saying? Like charges,
Oh, that they're reliably wrong?
yeah.
That's a good point. I don't think there's a way to capture reliably wrong to do better in this setting. Because if they're reliably wrong, their weight just goes down. They become irrelevant. You're not actually picking up, it's like, oh wait, if I flip their bit, I could do something with them. So you're not actually taking the expert answer and processing it in any way. That could be an interesting variant of this. Yeah, there's a question there.
So, in the modification for team, picking with some probability,
Yeah.
how does that compare to just taking the current best experts?
Oh, just the one that happens to be the best right now?
Yes.
It's much better because just taking the best one right now gives you no analysis at all because you can't guarantee progress. Because the best expert could have a weight that's much smaller than half the total weight. But the best single expert could have weight, I don't know, 1 over 10. And so you can't always guarantee they make progress or it'll make much slower progress. So it's always better to the weighted majority and it's slightly better to the randomization. It's never good to do just the single best expert. I suspect you can analyze it, but it's going to be worse than these. That's my feeling.
Yeah, I mean, I feel like, so we're taking some sort of weighted average of all of the experts, right? So in particular, you said you can choose some low weight experts and some. So it seems to me like that's just wasted.
It's not wasted because you don't, maybe you're a good maybe the best expert made all their mistakes up front. And if you don't allow them the chance to recover, you will never pay attention to what they're doing. That could happen. And eventually you might get up because, okay, suppose the best expert makes all the mistakes up front, they were hugely low weight. Time goes on, you futz around all the other experts who are just confusing you. Eventually this one rises to the top because they just depressed now, and you catch it. The problem is the eventually part. That if you took those early mistakes too seriously, what you're doing is you're waiting too long to recover and get back to it again. And that's what the randomization is trying to get you to do. To allow for the possibility that some of the mistakes of the best expert came early on.
Okay, yeah, I see that. But, conversely, you can have, maybe your expert,
Well, think about that. There's some more questions. Were there more questions? You had a question? Yes.
So this is cool, but it's not necessarily useful because of that assumption we made about.
This is cool because. Go ahead.
Well, it's because we made an assumption that there's always a best expert for the queries that we made.
Yeah.
However, that tells us nothing about how good they'll do in the future. At least we didn't analyze that.
Past performance is no prediction of future knowledge. So, I mean, but we're not talking about the future.
But
The game here, okay, the game here is I have a sequence of queries. And by the end of the process, I want to find the one expert who has done the best so far on these things. I want to declare a winner, if you wish.
why is
Or I want to go with the one who's the best on these so far.
Why is that useful? Because even if you have one that's a pretty good expert, it's an expert with respect to the queries you made.
Yes.
You may have a very small subset that happened to be, he was right a ton, but in reality, he was like one of the most wrong ones.
But what is reality? You have to define reality.
Yeah, and we haven't.
Only a theorist could say you have to define reality. I just realized that. So, okay.
Because we haven't talked about any probability distributions about
Right.
whether or not they're
So
correct.
if you wish to say, okay, we are going to build a model of the experts. This is their probabilistic behavior, and can you find them? You can do that. And that gets you to online learning and regret bounds and a whole bunch of wonderful things that you learn in machine learning. So machine learning, there's an area of machine learning called online learning, which is exactly the setting. Where the setting is where you have build some model, you make a prediction, you look at the answer, you check off right or wrong, and you go on. And a regret bound basically says, how did you do compared to the best single expert who was answering all those questions? And you can now throw in all kinds of priors and other things on them, and there's a whole line of work on that. Here, you should think of this as the problem itself being the sequence of queries. And we're going to see that in a second when we look at approximation algorithms. Think of this as an algorithmic design primitive, not as something that you actually want to do necessarily to poll your weather experts. But think of this as an abstraction. This abstraction will be applied to solve a bunch of problems. For example, you can solve linear programming using this method. You can solve semi-definite programming using this method. You can find equilibria of games using this method. You can do boosting. You can construct a strong learner from weak learners using this method. Think of this as a design principle. I mean, take the weather thing, don't take that too seriously. The zombies you must take seriously, not the weather. Okay, so I mean, maybe that is one way of answering your question. That the intention of this is not to sort of capture reality in its full form, but to capture an abstraction that allows you to do solution design.
So the piece of the abstraction that worries me is we measured the runtime in terms of the number of mistakes we made.
Right.
That's also an assumption that may not be useful, but I guess that's where all the other analyses you talked about come in, because just this by itself doesn't seem sufficient besides like.
Yeah, but think of an online learning setting, right? If you get the correct answer, you're happy. You're only unhappy. I mean, there's no time, right? It's an ongoing. Think of this as making predictions. You're always making predictions. You're a day trader. You're investing every day. You're happy when you get it correct. You're not happy when you get it wrong. I don't care how many days I'm running my experiment for. What I want to know is how many times I got it wrong. So that's why that is in fact the correct measure, I would argue, not the total time. The total time is not relevant. It's the number of mistakes you make that's relevant, because that's where you're paying a price for it. Okay. All right. So, of course, this can generalize even further, and many of you have already asked this question, why 0, 1, and why does it work this way? So let me show you how this generalizes even further. So in general, you should think of each expert. So again, we have the expert I. It has a cost, Mij. So there's a matrix, Mij, that captures penalties, and this is what we should think about. This is the Okay? So think of this answer space now as not just 0, 1, but as many possible answers. Let's say there are n possible, there are I don't know, k possible answers. Okay? So you have this matrix, right? So now you have this matrix for an expert, which will look like a k cross k matrix, right? And presumably there's no penalty for getting the right answer, and there might even be a profit. And there are answers on either side of this. Right? This is my MIJ. Okay? So you can generalize this idea of penalties and profits beyond just 0, 1s. You can make these numbers negative and positive. So you can have profit for getting the right answer and penalty for getting the wrong answer, not just penalty versus nothing. So that diagonal column could be something, it could be, -5, right? If you get the right answer. So that's like the penalty is -5, so actually your profit is 5. And you can do all kinds of things here. In general, we'll assume that Mij is some number between some negative number and so rho and L are two positive numbers. So when I say minus rho comma L, I mean it could be negative, it could be positive. So we'll assume in general this could happen. Right? And so the way you do the update now, you don't do the update as we did before. The way you do the update is you say that the weight of I at t plus 1 is equal to the weight of I at t times this weird quantity. And you scale it by rho. Okay. So let me try to unpack what this even means. Right. So have you ever seen what a matrix exponential is? Do you know what that means? I say e to the m, where m is a matrix. Have you ever heard this before? Okay, so it's a weird concept, right? So the way to think about the exponential of a matrix is to think about a Taylor expansion. So there's a little sidebar that I'm going to do here. So we'll first do what is e to the a. Because if I can do e to the a, then I can do c to the a is equal to e to the log c times a, right? So if I can tell you how to do e to the a, I can do anything. So we know that the Taylor expansion, or well, we might know, or we might remember, or we know now, that the Taylor expansion number can be written as, wait, do I know this? Someone tell me what this is. Let me see. Is this right? Okay? The exponential of a matrix is, oh, sorry. The identity plus I won't bore you with the details of how you compute this. Needless to say, in general, it can be very hard. But if you can compute the eigen decomposition of a matrix, then it's actually very easy. Because then you just take the inner diagonal matrix, the eigenvalues, and do e to the each lambda, and it's the same thing. So there are ways to compute this. But it can be hard in general. So. Okay. So that's what it means to do exponentials. So 1 minus, so in particular, 1 minus epsilon to the matrix will be equal to e to the log 1 minus epsilon, which is a negative number, times a. Okay, then just roll. So that's what it means. So let's go back to that example. So in general, if your matrix has more, if your penalties for your experts are more complex than just the simple, get it wrong, right? You write this in this following form. This is a little bit, again, harder to parse, but essentially, and I can assure you of this, it's the same idea. That you want to penalize things that are bad and encourage things that are good, but now bad and good are defined in terms of what's happening here. Because notice that if m is positive, your weight goes down. If m is negative, what happens? Your weight actually goes up. Because you're doing some number that's less than 1 to the negative power, which becomes a number that's more than 1 to a positive power. Okay, you can even think of this like 1 plus epsilon to the n, where it's positive. So we're doing two things. We're downweighting things that are bad, we're actually upweighting things that are good at the same time. Okay? And that's just the one change you make if you have generalized costs for matrices. And again, you can crunch through the analysis just like we did before. It doesn't change very much. It's just a little more ugly, but the idea is the same. You just look at these two things and you race and you see where you end up at. And the bound you get is going to look something like this. That the sum of the costs, the sum of the penalties, if you run this whole process for something like, let's see, log n over delta squared rounds, then the error, the average error. So the error you incur divided by the total by time is something like delta plus the average penalty. And the notes that I put on the website give this in gory detail, but the only thing you need to remember is this high-level understanding of what this is going to calculate. So in other words, if your experts have more complex reward functions, you can still do the same thing, and after a certain number of rounds, it's basically log n times an error term. Think of log n over delta squared as a real term, and the rho is just a scaling factor, so you can ignore that for now. The average error is going to be the average penalty of the best expert, which is the optimal solution, plus this extra term delta, which you cannot get rid of. Okay? So again, it's the same. Think of this was basically your n term here and your log n term here. That's kind of what's going on. There are a number of applications of this basic framework. Like I said, you can use it to think about boosting. So some of you have heard about boosting, know that the problem of boosting is basically saying, I have some algorithm that learns, but its error is very large. It's like, I get slightly better than a coin toss, and I have a whole bunch of these experts. And I want to put them together to create an expert who's really good, who's right most of the time. And the way you do it is by treating these experts as learning, and then doing this weighting of the different experts. And you can show that using the same analysis as I showed you, you can get an expert who's really, really good at predicting what's going to happen next. So this is what, when machine learning folks talk about boosting, this is what they're talking about. In game theory, you can think of this as the problem of finding an optimal strategy. So in game theory, you typically have some kind of matrix. You have the rows are one player, the columns are the other player, like in your zero-sum game, or in your prisoner's dilemma, or in your rock, paper, scissors, and things like that. And so you have to find some mixed strategy that is optimal for both of them. The attempt of finding a mixed strategy like this is basically can be solved using this method. Okay. The one example I want to show you, though, is from approximation algorithms, because that's something we'll be talking about a little bit. I want to show you how you can use this idea to generate an algorithm for approximating a particular NP problem. So the problem I'm going to look at is set cover. So recall the set cover problem, which I think I mentioned before. Your input consists of a universe, U, and a collection of sets, S1 up to Sn. And the goal is find a subset, Si1 up to Sik, such that the union of the Sij is equal to your universe. And K is minimized. So you want a collection of sets to cover the universe, and you want that set size to be as small as possible. Okay? All right. So here's the idea. Think of the experts as our points. And think of an event as a set covers a point. Okay? So in the beginning, so what you want to design some kind of algorithm that will find a good set cover. And so what you do is you say, okay, I have all my experts, they all have weight 1. Okay? And I want to make some decision based on these experts of weight 1. I'm going to find a set which covers as much weight as possible. So step 1 is find a set okay? So what you're saying is that I have a set that covers as much weight. That means in this case, I find a set that covers the largest set possible, because it covers the most number of points. I pull it out. Now, I want to penalize the experts, the points. But I don't want to penalize the experts that got it wrong. I want to penalize the experts that got it right. Because what I'm trying to do is, I'm not trying to find a single expert, I'm trying to cover all the points. So the points that are not covered are the ones I want to listen to. The points that are covered, they're covered. I don't need to worry about them anymore. They're done. They've been eliminated from consideration. So I want to find the problem expert, the one that needs to be covered, not ones that are already covered. So you downweight all the points that got covered, and you keep the same weight for all the points that don't get covered. Okay? So what you do is you say this. So downweight all covered points. So what's going to happen is now when you now pick a set that covers a lots of weight of the input, it's going to prefer to pick points that have not been covered yet, because their weight is larger. It's going to not prefer to pick points that have been covered already, because their weight is smaller. So then we can repeat. Okay? You can prove this algorithm will give you a reasonable answer, and here's the kicker. I said that I want to change the weights. So I said that the weight of a point, I, becomes the original weight times, 1 minus epsilon to some matrix cost. Now, keep in mind that 1 minus epsilon to the power of m, as an approximation, can be written as, if some things are small enough, 1 minus epsilon times m. Okay? And I will say that m of ij is equal to 1 if point I is contained in set j. So if a point is covered in a set, I will set epsilon equal to 1. What's going to happen here? If a point is covered in a set, that weight will get sent to 0. Because epsilon is 1, m is going to be 1, 1 minus 1 is 0. All points who are covered get set to 0. Which is what you think you would do anyway. Which is the greedy algorithm for set coverage. So what this does is it basically says, take all the points that you covered, set their weight to 0, which means you'll never consider them again. Keep the remaining points, find the set that covers the most of the remaining points, repeat that. So this algorithm basically becomes greedy. Cover maximum uncovered points at every step. Okay? Now it turns out that you can show. Here's the observation you want to make. This is where it gets interesting. So I want to show how good this algorithm is. So what I'm going to say is that opt, look at the optimal solution. Opt must cover all points. So if you look at the total weight of all the points, at any point you have the total weight of all the points, right? Since opt covers all points, and let's say it's like the size, the actual number of sets, we'll call it opt, there must exist a set that covers a 1 over opt fraction of total weight. Why? Because there are opt number of sets, the total weight is whatever. By Pearson's principle, there's one set that covers 1 over opt of this weight. If there's a set that covers 1 over opt, we're being greedy, we're finding the best set possible, we're going to find a set like this. how much does the weight reduce by? Well, if it covers 1 over opt and that weight gets sent to 0, the new total weight becomes the old total weight times 1 minus 1 over opt. Because we took all that 1 over opt weight that set covered and we set it to 0. Okay? You can rewrite this expression as and since the original weight is n, this process must converge in opt times log n steps. So, and since you pick one set at every step, after opt times log n steps you've converged, therefore the number of sets you've produced is opt times log n, your approximation ratio is log n. So in other words, if you take and approximate a problem that you want to solve, and think of this as a linear programming problem, your constraints are telling you what you need to satisfy. So you start off with none of your constraints satisfied. Okay, you get some solution, some of the constraints get satisfied, you set their weight to 0. All the constraints that are not satisfied, you increase their weight. And you keep doing this over and over again. There's a huge class of problems, of linear programming problems, called packing covering problems, which can be solved using exactly this framework, the multiplicative weighted weight framework. And you can get a provable guarantee and approximation ratio for them on. It depends on the particular problem what the approximation ratio is. In this case, you get log n. So the other reason for this hammer, this multiplicative weighted weight hammer, is that you can now apply it to many different problems where you didn't know how to take the linear program or do anything with it. And it produces an algorithm all around. And what you stared at becomes, like in this case of set cover, a very simple algorithm. Okay. So let's go back to the beginning. So we saw the binary search connection along with its zombie friends. We saw the connection to linear programming via set cover. That set cover basically gives you this way of, is an example of how you have a problem, you have constraints, you need constraints to be satisfied, you keep updating the weights of constraints that you're not satisfying, and you keep making progress now. And again, I mentioned briefly that you can think of this in terms of boosting, strong learners and weak learners, and also in terms of getting more. The notes have a bit more examples on all these things. So if you look at the new notes I linked to, they give one example of each of these categories to show you this. So again, what I want you to take away from this is that this is, again, a design tool that is like a sophisticated version of binary search with errors. And that can be applied in very non-trivial ways to all these settings. And so something you should keep in mind when you have a problem you want to attack with this particular tool and say, okay, what tools are at your disposal? You should keep in mind this other tool is also available to you if you can put your problem in one of these settings. It's kind of learning from experts type thing. All right, that's it for today. I will see you all next week. Okay.